The tail is not picking it up. If you turn it into a regular file, the tail will pick it up. Yep. So it's only when it's a pipe that it doesn't pick it up.
I think so. Like when you call write to a pipe, it will actually write unless something else is reading it. And then I don't think it thinks tail is reading it.
So tail-f is not considered reading from the pipe.
I don't know. Maybe it's because it's not read-write capability, and cat might be.
Okay, we'll just use tail pipe instead of using tail pipe out. And then do that again.
Because I had the same problem, and I thought
that didn't work either.
My program not working. I started using cat instead.
So somehow cat works differently. That is interesting. Because I got it working, in my office before I uploaded the program. So it must be the order of, doing things. Okay. I just separated that into its own terminal. If I turn this back into cat, then it works. Yep. So cat works, but not tail. Cat, tails, tail pipes, cat tails. So use cat instead of tail to test the program. I mean, that seems to be the easiest solution, is to use cat instead of tail to look at the output of the file. Tail-f works really, really good with regular files, but for some reason it just doesn't work well with pipes.
I think I might know why.
Yeah, go ahead.
Tail might not read the pipe unless it thinks something's been written to it. And so since nothing gets written to it while no one's reading it, then it just never has anything to read.
But cat, on the other hand, that actually just opens the file and try to, pump the content back to standard out.
Yeah, that's just a guess.
Yeah, tail-f is a polling mode. It checks for the size of the file and reads from the end of it.
And not anymore. Now it's notify enabled.
Oh, cool.
But still, that's what
tail-f.
what's the dash F do?
Sleep interval between iterations. Okay, with follow, tail defaults to following the file descriptor, which means that even if a tailed file is renamed, tail will continue to track its end. This default behavior is not desirable if you want to track the actual name of the file, not the file descriptor. Use file name. So that has nothing to do with what we were seeing. And then being lazy, where we'll look for FIFO. Nope, nothing specific about file or pipes. So the tail command do not treat FIFOs any differently. It's just that the mechanism it uses to keep track of the file doesn't make it does not work well with the pipes. Okay, well, use cat instead of tail. And I will probably try to explain that because I just can't stand it when it doesn't do that sort of thing when it's supposed to. Okay. Any other questions about the using of pipes? No questions? Okay, so we can continue to talk about p-threads. And we're using the external file or the external link at this point. This link comes from not Los Rios, but Lawrence Livermore National Lab. So someone in the lab obviously has to explain this one too many times to colleagues and decided to write something and just send all the colleagues the URL. We have already talked about some parts of it. We talked about why p-threads because of the efficiency difference between processes and threads. So we talked about that already. I also gave you guys a pseudo, program, which means it's not actual code, but a thread is kind of like a subroutine that is on its own. It is executing, its own function on its own that is quote-unquote separated from main, which also means that it needs to have it needs to have its own stack because all subroutines in C need to have the stack to store the local variables, parameters, and return addresses and whatnot. In other words, we have covered at least this part here. We looked at the table, and then we realized, in order to create a P thread, which means POSIX thread, the amount of time is about 1/10 of the amount of time that you need to create a new process. So creating a new process is a much more costly type of operation compared to creating a thread. Okay. So here we have a whole bunch of discussions. Also, all threads within a process share the same address space. Inter-thread communication is much more efficient and in many cases easier to use than inter-process communication. Now that is an interesting argument point because Christ has illustrated how you can use memmap. Is it mmap that you used? So the two processes can share the same memory space as well. So you can, if you want to, use shared memory for processes to talk to each other also. In other words, this is convenient and efficient in the case of a thread. In the case of a process or two processes, it can be done, it is just not as convenient. It is not by default sharing any memory space, but you can make processes share the same memory space if you want to. Threaded applications offer potential performance gain and practical advantages over non-threaded applications in many other ways. Overlap CPU work with I/O. For example, a program may have sections where it is performing long I/O operations, while one thread is waiting for an I/O system call to complete. CPU-intensive work can be performed by other threads. But this is really just comparing, threaded programs as opposed to programs that are single-threaded. Okay, it's multi-processes. If you have multiple processes, this can still be done. Okay, it's just that the communication between the processes is a little bit more problematic. Priority real-time scheduling. Tasks that are more important can be scheduled to supersede or interrupt low-priority tasks. This also has nothing to do with threads versus processes because you can also schedule processes according to priorities. So that's not an advantage of threads over processes. It is simply threaded programs versus non-threaded programs. Let me ask you a question. If you don't know anything about how to make parallel processes or parallel threads, how do you keep track of multiple things at the same time? Let's just say that you're making a robotic type of application program, and the robot needs to keep track of many different things, including it has to monitor the motors, it has to keep track of its location by reading the GPS, the feedback from a GPS sensor, and it also has to process, some sort of video input from the video camera. With a single thread program without processes, how would you do all those different things, so that the robot seems to be able to look at the video camera, do the navigation, keep track of where it is, and many other things?
You could use polling. Could you use polling?
You can use polling, but each one, each subtask that you have to perform, it may take too long to process the entire frame from the video camera, and the other stuff will need some time to execute before that is done. In other words, okay, let's say processing a video frame for certain things takes 50 milliseconds. But on the other hand, you want to monitor your motors, okay, the encoder from the motor, every 1 millisecond or so. So how do you do that? In other words, let me just draw a picture to make it a little bit more more clear, because I do want to point out the advantages of a program that is multi-threaded or multi-processes, or using multi-processes, as opposed to a single-threaded program. This is time. And processing one single frame from the video input, let's just say that it takes 50 milliseconds. Okay, so this is frame processing. Okay, so every 50 milliseconds you process one frame, another frame, another frame. And 50 milliseconds is chosen in this case because most video cameras will give you about 20 frames per second, which translates to 50 milliseconds between frames. 1 second divided by 20 is 50 milliseconds. But that's a very long amount of time.